Anyone know what do these three computers have in common besides being from the 80s? Anyone? And what was the processor? Applause to Minus. Thank you, thank you. Yeah, they actually do have, and that's my. Let's not give that away, but see if I can get my. Now there's. So okay, the talk. Surprise yourself with property-based testing. I already asked you. Obviously, I'm the Amiga guy, so that's why it's the biggest one in front. But you're right, it's the Motorola 68000 CPU. I didn't think someone would be old enough to remember that, but yeah, perhaps I'm too pessimistic. So why is this relevant, you might ask? It ties into why I and what got me excited about property-based testing, actually. So, and if I may complain, this screen isn't showing. Okay, I can look here. So what got me inspired to try out PBT? I wanted to try Rust. This was a story for like 8 years ago when Rust came out 1.0. I wanted to write something. So I wrote, hello world, as you do, and then as you do, you write a CPU emulator to see if you understand something. So I started writing a Motorola 68000 emulator in Rust, because that was the coolest chip of the 80s, early 80s at least. So I did not start from scratch. I had an inspiration, which I had used a little bit before, which is a library called Musashi, which has been running code in the MAME emulator framework, so you can run emulated arcade games in it. So Musashi was already successful in running existing applications with 68000 code. So I just thought, okay, I do sort of a port of that. So I'm part of the, rewrite everything in Rust crowd. You can hate me for it, if you like. So there's the repo, and I'm going to try something. I'm not sure if I'm shooting myself in the foot here, but I'm going to try to add QR codes to a couple of the slides to see if you want to go to the repo, it links to some additional material and so on. And please don't get too lost in your phones, right? Okay, so also I noticed this has a connection to the Øredev team, the Halt and Catch Fire, because you shouldn't really listen to what the people at Øredev say, what it's all about. The burning to the ground stuff. That's just history revisionism as far as I'm concerned, because it's actually an additionally undocumented instruction on the precursor CPU to the 68000 that caused the processor to go into an unrecoverable loop, right? So they jokingly nicknamed that the HCF. So if you pull up the instruction manual for the 6800 now, you will see HCF for that instruction. Anyway, testing such emulator. There's 56 instructions. Add, null, jump, and so on. But those are sender mnemonics, right? So underneath those are opcodes. So I thought, let me write a few example-based tests for one opcode. It shouldn't be too hard, but there's a combinatorial explosion here of instruction variants. There's different adds, for example, add with address, add with carry, add with this and that. Data sizes, registers, addressing modes, and so on. So in theory, there's 65,000 opcodes, but only 54,000 of those are actually valid, and about 4,000 for the adds. So I started realizing that, okay, example-based testing, this is going to be hard to cover a lot of the cases. So it was here that I realized that I probably needed something else. And I was, in like your situation, I had heard of property-based testing, and thought to myself, maybe this is a good place to try it. I hadn't tried it before, so let's get back to that later. But now I just want to make sure that we understand what we're talking about when we're talking about property-based testing. What kind of properties? The JavaScript object property? Is it? What is this? So it's sort of a claim about something. And as a thought exercise, we can think about properties of water. Okay? So anyone can name me a property of water, please? Wet? Liquid, perhaps? Anyone else? Yeah. Sorry? Yeah, it's a solution. It boils at 100 degrees and so on. And sure, that's true. But if you think about it, it's not always a liquid. It's not. Is one molecule of water, is that wet? Is the boiling point always 100 degrees centigrade? No, it's not. Depends on pressure and so on. So what I'm saying is that not all properties are universal. There's conditions that apply. Are we talking about bottled water? We could talk about carbonation and flavor and cap color and whatnot. So it depends on the context, right? So let's compare now a little bit about example-based, which is what you know and love and I hope use, versus property-based. And as a comparison, I think that one of the risks with example-based tests is that you're sort of limited by your own imagination or perhaps experience, how you want to put it. Because if you didn't think about, say, nulls and negative values and zero-length strings and whatnot when you wrote the tests, you probably won't sort of put that in your code and vice versa. So it's easy to mistakenly do happy path examples. But I think that property-based tests, they are very good at surprising you and your code. And they, in my mind, have the potential to greatly improve quality and robustness. And especially for libraries, I think, because if you have a function, you're only calling it in the context of your own sort of domain, you're the only client, so to speak. Then you know the domain of the things coming in, and you might not need to handle Japanese UTF-8 encodings and whatnot. But if you have a library and you put it out to the code monkeys and they will throw bananas at it. So we will, especially for libraries, I think. And I think we could now look at how it looks. And this is, if you start by doing the simplest possible case, and let's run with an example here. I want to calculate sound volume based on some parameters. Let's call them amplification, pan, and reverb. It doesn't really matter. It's just an example. But let's say we have that, and that we know that if you just put zeros everywhere, the expected volume should be zero. So you implement that case, and you start going to a somewhat more complicated case, and then, another one. And then sometimes not you, obviously, but your colleagues, they will stop here and say, there, these tests are fine, they prove that my function works. Let's go on with the next feature on the next Jira issue, right? Possibly you will write something in the more data-driven style. And if I was a tech lead on your team, I would encourage you to write something like this. But if I ask you now to do, I need 100. I'm not sure you have implemented that correctly. I need 100 examples. If I ask you to do that, you would have a hard time, especially with the expected values, right? I mean, what's the correct answer? Maybe you would run it through your sound volume calculation to get the correct values, right? Because then it passes immediately. That's right. No, don't do that. That's a big pitfall. But you might have an old system. You might use Excel. There's a certain formula in a book, and you can calculate it and whatnot. Doesn't really matter. But you can agree that there's some effort to writing these down, right? So if we contrast that a little bit with property-based tests, and let's say we have a property about our sound volume function calculation, But we know that it's not possible for the volume to be negative. I mean, what does negative volume even mean? So we can write a property. It could look like this. Takes in the parameters and call the functions and assert on it. So then we could write sort of the data-driven version of calling that, right? But now you notice that you don't really need the expected values here, right? Because you're not actually expecting the exact, precise detail. You're just saying it should never be negative. So now, if I ask you, as the tech lead, please write me 100 examples of this, it will be much easier for you, right? You could even, if you knew these were sort of bite-sized values, you could possibly even loop through the input space. Or if the input space is actually full integers, maybe you couldn't do that, but you could do a subset of randomize some data. Give me 1,000 ones. Okay, so now it's a bit confusing, right? Because is this a data-driven test, example-based test, or a property-based test? I think it's a bit of all of them. So what then is the difference? Perhaps there's not too much difference. And if you don't use any tooling, right, then I think this was property-based testing. But we can do better than that. And if we look at this game, the Lost Diamond, anyone play that? Yeah, you've seen it. If we think a little bit about from the keynote, this is a very Western-centric view of. It's the British Museum version of Africa, because the goal of the game is to find the diamond, and then it's yours, and you win it, right? So. The diamond will be at any one of these red places, and you search the board for the diamond, right? The diamond is called the African star, I think. But so this is a kind of a search problem, and if you're playing this game, imagine you are example-based testing incarnate, and you are playing this game. What happens is that when it's your turn, you pick 5 of these. And check those, and if you found the diamond, you won, you found the bug, but if you didn't find it, okay, I know that these aren't the ones, but next time it's your turn, you don't even roll the die, you take the same 5 and check those, right? And the next time you check the same 5. So it's a good verification strategy to check some known points, but it's a bad search strategy. I think you can agree. If we roll the die with property-based testing, search Africa for the diamonds or your code for bugs, I think that's a better approach. So what could we expect what kind of support could we expect from property-based tooling if we had that, which we do? I think it helps you optimize the search through input space. And typically it has 2 to 5 components. Some of them only have 1, the random part, but yeah, the random part is called generators. So I haven't seen a framework ever that doesn't support the random part. So I think every library supports that. I'm going to show you some examples later in code, but most, if not all, what I'm saying is sort of applicable to kind of any language. Okay, generators. They're the ones that give you random integers, random strings, and you compose those to get sort of random persons and then random invoices and whatnot. So that could be tricky to get a random invoice correct, but you can start simple. Second thing that most libraries support is something called filtering. That is to give you the power to ignore some irrelevant situations. We know that if you call my function, the volume calculation function, with negative numbers, perhaps that's not sort of an actual use case. So let's filter those out. A very important part is the stateful tests. They give you a random walk through an API, and it's really, really powerful. We will show that later. Shrinking is sort of when you find something randomly, it might not be the simplest example you find. So shrinking is about getting the minimal reproduction of that case. And there's also some of the more advanced libraries have race condition testing with the custom schedulers and so on. I won't talk about that more than this. So this is going to be a complicated slide, but let's stay here a while and see if we like it. So if you want have a property, let's say the volume is never negative property, you would generate some inputs, and you would check the precondition. Perhaps you had this precondition, you should never be negative. So if one of the generated values was negative, you could discard that test case. But in practice, if you have it should be a prime number, and you just ask it to generate any integer, and it's not prime, and that's not prime either. That's your sort of wasteful way. So then you would have a custom generator, or you have a range. You constrain the generator somehow. But sometimes it's hard to do that. So then you have the preconditions, and then you actually call the function, in this case, the calculate sound volume, and you perhaps in some cases it legitimately throws an error because some combinations aren't meaningful. And then you could say, okay, I wanted to define this property only over the actual result, not over the exceptional cases. So I won't consider this an actual test. It also discards. And then we go, if we pass the post condition, we check that the property holds. Have we found a counterexample to water being wet, or have we not? And if we have found that it doesn't hold, we fail the test, and we try to shrink the result. And I will show that a little bit later. But if you do pass the property, what typically happens is that you go back up to the top and check, have I gotten sort of 100 passes, 100 random inputs correct? And if you haven't, you keep doing that until at some point you have gotten enough. And that's obviously a configurable parameter to how many tests you want to pass. So basically, run through, fail, or pass. I mean, that's not too interesting, but the interesting part is that there's some ways that you can discard some invalid cases. Otherwise, you would have a lot of sort of noise in your verification. Okay, so this is what if you use TypeScript and a library called fastcheck, this is what sort of a test for. I can see if I can point. Yeah, I can. Anyway, the calculate sound volume function here, I will. Here we have the green text is the 3 random inputs. And you could have written this like we had before with the property I defined. But yeah, so let's say I did this and ran this test. I would get something like this out, a jest error. And let's zoom in a bit on what it actually says. It says, I found a counterexample. If you call your function, and the QR code goes to sort of the test classes there, and you can navigate if you want to the actual implementation. But what happens is that if you pass it 385, a value turns negative, and I use the square root of some value, which means that I got not a number back, square root of a negative number. So, and 384 passes, but 385 does not. So how did it know that? Well, if you look at if you can ask fastcheck and other libraries to be verbose about how they got here. So what it actually did was, the initial failure was something like 491 million for the amplification, 764 million for the pan, and minus 21 for the reverb part. And then it starts to shrink those by sort of divide by 2 strategy. So you see it starts shrinking the first parameter, then it gets that down to about 5, and it starts to shrink the second parameter, and it then starts to shrink again. The third parameter gets down to 0, and then it eventually tries a little bit more, and then it ends at 385. In this process, it will have generated successes, so to speak. It tried with a value lower than 385. Oh, that passes. Okay, that couldn't be the problem. So let's back up and sort of narrow down to what actually happened. So, but if you run it again, it won't necessarily give you 1,385,0 because there's other cases. If you have a big negative number in the middle, for example, that also gives you the same result. Okay, that's shrinking. Now on to the sort of the really meaty part of property-based testing for me. At least I think stateful property-based testing is really, really powerful. And I try to show you this with a oversimplified example that won't show you the power. So that's why I have a story that gives you sort of a better view. But let's say we have a stack implementation. Okay, let's call it BOGO stack. I botched it, the implementation, on purpose. So we'll see if it can find that. But it has 3 commands or 3 things it can do. You can push something, you can pop something, and you can ask it for its size. And the yellow part here, the size, that's the model, the state that you're trying to compare with. So this has support in some of the libraries. I think it's hard to do example-based. You could do sort of a random walk, manually implemented, sure. But then you would sort of duplicate work in this space. So what would happen if we sort of just thought of our state, the number? Let's say you push 3 times. Yeah, we expect the size to be 3. If you pop it, we expect the size to be 2. And if you ask it the size in that state, you should get back 2, right? So it's not complicated. We don't even care what's in the stack. We only care at this point, this particular property we're writing, only cares that it knows that the state seems correct, matching what we expect the stack to actually hold. And let's see what we sort of, how we implemented that as a test. So the first thing that happens in a stateful test is that we pick a command that is valid for the particular state we're in. So let's say that in the initial state, you can't pop. So we won't generate pop commands. So the first command is going to be ask it to its size or push something. And then we check if this, the preconditions and postconditions and so on holds, and that the number seems to match what it says it should be. And if it doesn't, we have found the problem, and we go to the shrinking phase and fail the test. But if it actually does match, we try again. Perhaps we walk 100 times here. So the point is that this is different from the previous test because we have a state. We use the same instance of the BOGO stack to manipulate. We do a lot of pushes and pops and ask it for its size. So it's the same instance we just keep poking at. We're not running each test with a fresh instance, right? So what I did, obviously it passes when it passes. So this is how you would write that in fast check. You would say something like, assert the property that all commands should follow this property. And the size here is how many steps should it generate. So this is, if it's going to run 100 or 1,000 steps. There's our state, the 0 state initially, and we start with the real model. The real implementation is the BOGO stack. And then you sort of ask it to run with the command array you had. And if you run it on my BOGO stack, it will fail because I actually said that if you push 10 items onto the stack and then push the 11th, it will reallocate, I imagined. And then it adds another, storage for another 10 items, but it also messes up the size calculation. So if we zoom in a little bit here, we can see that what happened was that it did 10 pushes, then the 11th push triggered my imaginary, or rather explicitly written bug, and then it asked it for its size, and then it noticed, this doesn't really match up because I expected it to be 11 items, but it was 21 now. That couldn't be. So if we ask it now, what was the initial example, okay, that you found. It didn't find this right away. The first thing it found was a sequence of 34 commands starting with an enormous blob of things with big numbers, a lot of size and push and pop. And we know, as I told you, the bug, we know that the intermediary pop and size and stuff, that's just irrelevant stuff. The numbers are also irrelevant. So if someone came to you with this repro, yeah, what are you on? You would say. So, and the last thing is that he pushes the 11th item onto the stack and asks for its size. That's what actually happens then. So what I think it's quite impressive that it then managed to do more or less the very clean, minimal repro case with just push zeros 11 times and then check for size. Nothing irrelevant. So the story that is probably going to sell this a little bit better than a fake stack with a bug in it is a story told by Joe Norton in 2013. He wanted to try out property-based testing on a Google product called LevelDB. It's a key value store. So he did the same thing that we did with the bogus stack. There's a couple of commands. You have the open and close database, put and delete and seek. And he ran this. And the model was basically just a key value dictionary in memory, nothing fancy. So he ran this and found a 17-step sequence where you opened, you closed, you deleted, you inserted, deleted the same thing again, and so on. And then suddenly a key you just deleted reappeared. Oh, I can find this key, but it should be deleted. That must be a bug. So he sent it to Google, and they issue a fix for that. Okay, so let's move on to some criticisms of property-based testing. This is the enterprise people. They will want to know, they don't want unstable tests, they don't want to be uncertain who broke the build, and they don't really like it if the builds aren't reproducible. So introducing non-determinism in that environment could be problematic. I mean, if you have the problem that you do a bug fix, the test now passes. Was it your fix or was it the random walk that didn't actually trigger the bug again? And the opposite, if you had a feature, the test now break. Was it your fault or was it, the random walk that fixed it, that detected something it usually doesn't? So what you can do as a sort of concession to the enterprise side of things is you could, most libraries have the possibility to freeze the random number generator seed, so it will only generate the same steps. And you can see that it works on your machine, it will work on the CI machine as well. Obviously, you drop the search part and you only do the verification part, right? So that could be a problem, but you can also move the non-deterministic parts to, say, a nightly bug hunt that could run for as long as you want. You could, the parameters, how many steps you want. I want 1,000 steps, and I want to test it function 1,000,000 times. Could have a couple of hours of fun, burning some carbon, right? My advice is really to try to, if you're going to this route of property-based testing, I think it's non-determinism is a feature, not a bug in this sense. So if we go back to my project, the R68K project in Rust, I did a couple of properties, but mostly I did one single property that was almost all the work. I had a library, right, that I thought was battle tested and working, and I re-implemented something and compared the results. So what I did was I set up a random initial state and execute in both systems, in both the Musashi one and my library, right? So memory, random patterns, and CPU flags, and random patterns, registers, random stuff in it. Execute one instruction and verify that the resulting state is identical. And again, we need to analyze what the problem, if there's something that is found. We can't be 100% certain that it's my fault. Obviously, battle tested versus I wrote 2 lines of code, probably my fault in the beginning. But at some parts, you really need to analyze what is the correct behavior. So the outcome, if we look at a little bit of that, I wrote something like 1,600 quick checks tests. And the reason I didn't do one big test that tests all the 65,000 opcodes in one go, because it would have generated an enormous amount of noise in the beginning when I just had implemented add and nothing else. You haven't implemented null. I know. So I stripped it down to 1,600 individual small things and asked it to compare. Okay, so now it covers what I think is all possible cases with hundreds of trials each. It's Musashi, the library I used. It's single-threaded. It uses long jumps around the code and the global variables and whatnot. So you can't really run it multiple instance. So the runtime of the tests is about 4 hours on my machine. And it found many odd edge cases that I didn't anticipate myself. And I fixed my bugs, but I did also 16 PRs against this battle-tested library. And to be fair to Musashi, only 1 or 2 of those were actual sort of CPU behavior bugs. Most of them was in the internal accounting of, because what you do is you give it, please run 100,000 clock cycles, emulate that. But it miscalculated a lot of the costs of the instructions. And I had the Motorola manual. It should be 45 here, and my code says 45, so it's probably a bug in his code. What I also learned is that properties can evolve. I think this, I initially thought that, yeah, you're right, as you do with your example-based test, you have it live there, and then you write another thing to grow it, so to speak. But in this case, I had the property. Initially, I could only, if I remember correctly, I can only check the registers matched. So I run the instruction, do the register values match in both systems. Yeah, fine. So then I fixed some bugs, and then I got around to implementing more of the memory subsystem, so I could then try to get it to compare the memory accesses. We have a 32-bit write here, and the same here. We have a 16-bit read here. Now I have sort of, without modifying my 1600 tests, the completion test for the property comparing is more granular. Tests more things: CPU flags, memory, status flags, and so on, and registers. So I think it was an enlightenment for me that I was thinking that it would be static, but you can improve these over time. So this, I think, is the part that you're going to rewatch later, because I will say a lot of things and you will say, yeah. But then you sit in front of your computer and want to try out property-based testing, and you will sit there, okay, what's the property of my invoicing routine? I don't know, but is it wet? I haven't got a clue. So let's just help you a little bit along the lines of what you can think to get some properties. And the link here goes to the test repo README where I sort of outline all of these. And I probably will do a blog post or something about it at some point. But yeah, so there's 3 things: facts, inverses, and known good ones. That was the one I used, the known good. I had the Oracle version of the library I can compare with. So let's go through this in a little bit more detail. And it's going to be the same QR code on all of these fact slides. But my point is, I can tell you now, you will forget it, you'll come back to this later, but practice makes perfect. So it's hard to come up with your first few, but then it gets easier. You know what helps and what isn't helpful. Okay, so what we can do is ask for something general about the result. That's what we did with the calculate sound volume, and we did the property should never be negative. That's about the result, right? We can also look at something about the result in relation to the inputs. So I gave it an array of 21 items. I expect an array of 21 items back. You could talk about observable side effects. You run the invoicing routine. Now the total amount invoiced should be greater. Okay. You could also say something general about the execution. And that's what sort of fuzzing tools do. They typically try to make your program crash in some way with malformed inputs. And even if you don't have the power to sort of generate any random input, you could check that it doesn't throw an exception at least. Okay. In general, anything you'd write an assertion about without even thinking about property-based testing, you could write that as a property. And you could also, with great benefit, sprinkle your code with assertions. This should never happen, and this should always be positive, and so on. It helps your properties to verify. And this is very similar to the idea of design by contract by Bertrand Meyer, who wrote an entire language to support that. Okay, now let's go on to inverses or duals. I think it's easy to understand. If you have something that encodes something and you have another function that decodes the same thing, we should get the same thing back, right? So you write something, you read it again, it should be the same thing. Encrypt, decrypt, serialize, deserialize. Write something and then you delete it. It shouldn't be there, as if it wasn't there at all. Do undo is the same thing. You have an order, you cancel the order, and so on. Lots of examples, but these latter ones that do and undo stuff, you have to be careful that, because a no-op will satisfy that, right? You didn't write anything and then you didn't delete anything either, and it's still the same. So you need to check then that the write actually did anything. Probably you have some other tests that do that, but just as a reminder. The known good one is very productive, I think. That's the one I used with existing code. So perhaps you have an old version, you know, your legacy code. I hate that system. It's too slow, but it works with the invoicing stuff. It's really good. That's the correct thing. We need to re-implement that. Perfect case, in my opinion, if you can ask it stuff. Third-party libraries, the one I had used, also a good source of the truth. But anyway, really, to get automate getting the correct answer. So it doesn't really matter what you do. And you can even do it manually. This is what I have done sort of mostly, because some legacy systems aren't really talkative. They don't have the API you expect. So you go into a test in the legacy system, you ask it to do stuff and dump out the results to JSON or something. Then you do the sneaker net thing and move it to your computer and run the same things there and compare. That's a very manual process, but it's still sort of using the known good values, the correct ones, to compare. A property should be the same. Okay? So, but in some cases you don't have an old version of the code. You're writing something new. And what you can do then is implement two versions. I mean, like in, what is that movie with Judy Foster, you know, 2 for the price of 1, the Cosmos, is that? I forget. Anyway, so you implement the real one that you are intending to use in production, but you also implement one that is such obviously correct, if that is ever possible. But it could be very idealistic, that one. Could be, as we had an example, a database could be emulated as an in-memory dictionary. Yes, and it could be not thread safe or persistent or anything, and it could be unoptimized. So doesn't really matter. The thing is that you have your production code which has this hairy optimization, and then nice and clean and correct, one was slow. Then you can compare those. Okay, these are the last few slides. Wikipedia page says that 40 different languages and 57 different implementations of quick check and other property-based testing tools. The QR code doesn't go to Wikipedia. I expect you to find Wikipedia yourself, but it goes to a page where you actually compare some of these libraries with the features I mentioned with shrinking, stateful tests, and so on. So it's a quite good resource, I think. Now, obviously, you have been here. You are all convinced, but you need to sway other people, perhaps. So have them look at this presentation, perhaps. You could look at qvik.com. They provide commercial property-based testing tools. There's a lot of conference videos, particularly John Hughes, which is the chairman at qvik and the inventor of QC, one of the authors at least, works at Chalmers. I think the QR code goes to, I know the QR code goes to his talk, testing the hard stuff and remaining sane, which is a great talk. You should also look at the testimonials page for hypothesis and the track record page for fast check, just to get some arguments if people think that there is not going to be anything. So let me return briefly. This is the last slide. Let me return to the LevelDB story, which is they released a fix, Google, came back with the same unmodified test. He just ran the same quick check test again, and it's found that the bug wasn't quite fixed because it now found a 33-step sequence through the code that also reappeared deleted keys. So that's an interesting story, I think. But very much thank you for listening, and my blog and some places to reach me. Thank you very much.